Dear students, we know that as per the definition of electrostatic potentials, work required to be done against the electric field in bringing a unit positive charge from the infinite distance to given point in the electric field is called the electrostatic potentials. That is denoted by V. Okay, means work done by the electric field is given by the formula work infinity to P E into dr. If we want to find the work required to be done against the electric field in order the motion becomes the motion without the accelerations. The formula V W infinity to P, that is W dash work done infinity to P E into dr, but against electric fields that is a minus. Okay, an important characteristic of an electric field is called electrostatic potentials, and with the reference to be work done on the unit positive charge, it is defined as under the work required to be done against the electric field in bringing a unit positive charge from infinity distance to given point in electric field is called electrostatic potential at that point. Equipotential surfaces and potential surface is that the surface on which the electric potential at all points are equal. The electric potential due to the point charge is given by the V is equal to KQ by R. This is the potential due to the point charge. If R is constant, then V also becomes the constant. Okay? For this we can say that for the single point charge Q, the potential surface are the surface of the sphere drawn by the taking this charge at the center. Means suppose positive charge है. Now this is the electric field line generated by the charge. This is the equipotential surface. The potential on two such different surfaces are different, but for all the points on the same surface, the potentials are equal. The electric field produced by the point charge is along the radial directions drawn from it. Positives रहेगा तो radial directions going और negative रहेगा तो directions coming directions. ठीक है, पॉजिटिव डायरेक्शंस तो ये डायरेक्ट पॉजिटिव चार्ज तो डायरेक्शन आउटसाइड रहेगा और नेगेटिव रहेगा तो डायरेक्शन इनसाइड. One equipotential surface, this is the one equipotential surface. Okay, and this is the equipotential surface, and this is other equipotential surface. Okay. These radial lines are normal to the equipotential surface at every point. Hence, at a given point, the direction of the electric field is normal to an equipotential surface passing through the point. We said now to prove that this is true not only for the a point charges but in the general for any charges configurations. Suppose a unit positive charge is given a small displacement that is dl. Small displacement that is dl on the equipotential surface along this surface. From a given point in this process, the work required to be done against the electric field is dW. Okay, the small displacement work done, small segment that is dW is equal to, according to the definition of the electrostatic potential, that is V is equal to minus E into dl. So that is dW is equal to minus E into dl. As per the definition of electrostatic potentials, that is V is equal to integrations infinity to given point E into dl. This is the potential difference between 2 points. But the potential difference on the equipotential surface is 0 because सभी points पे potentials कैसे होंगे same. So the potential difference is 0. Means E into dl is 0. Equipotential surface is 0. So this is 0. Okay. Here dot. This is E dot means that is cos theta. E dl cos theta is equal to 0. Here cos theta represent the dot product where theta angle between E vector and dl vector, but E does not equal to 0. Okay, dl does not equal to 0 because we have equipotential surface, means we have the electric field, we have the small segment of the elements, so this does not equal to 0. तो क्या रह जाता है cos theta is equal to 0 means therefore cos theta is equal to 0 means theta is equal to cos inverse 0 means theta is equal to pi by 2 means we can say the E vector and the dl vector is perpendicular means E vector perpendicular to the dl vector, but dl is along the surface, hence the electric field is normal to the equipotential surface at the point. Like the electric field lines, the equipotential surface is also a useful concept to represent the electric field. For a uniform electric field prevailing in x directions, this is the actor prevailing in the x direction, is normal to the equipotential surface at the point. This is the surface and this is the electric field lines. Okay? This is the perpendicular to the normal. Okay, students, the most timely topic of this part 1 of second chapter, that is the relation between electric field and the electrostatic potentials. We know that the potential difference between 2 points, that is VQ minus VP, that is the potential difference between Q and T, so that is delta V is equal to minus integrations P Q E into dl or E into dr. Now, if the point P and Q are very close to each other, then for such a small displacement dl, integration is not required and only the one term E into dl can be kept. Means small segments के लिए delta V is dv, integration required नहीं है, means that is E into dl. If dl is the direction of E vector, okay, if dl is in the direction of E vector, so the E into dl, that is cos theta, and the cos theta same directions, that is a 0, means E dl same directions, so that is cos 0 is 1. So this is dv is equal to minus E into dl. Therefore the E electric field is equal to minus dv by dl. Okay, these equations gives the magnitude of the electric field in the direction of the displacement dl vector. Here dv by dl is equal to, means dv by dl means the potential difference per unit distance. It is called the potential gradient, means the potential gradient is dv by dl. The SI unit of the potential gradient volt per meter. Okay, or the SI unit of the electric field is written Newton per coulomb or volt per meter. Same for the x directions, electric field with respect to the x axis, so that is Ex is equal to minus dv by dx and Ey is equal to minus dv by dy. Ez minus dv by dz means we can say the E vector is equal to minus dv by dr vector or dl vector. Here r is the component of x, y, z means that. Dear students, if we had taken the displacement dl not in the direction of the electric field, means dl is not in the direction of the electric field, but in some other directions, then dv by dl would be given the component of the electric field in the direction of the displacement. Means if the electric field in x directions only and the displacement is in any directions in the three dimensions. So the E vector in x directions, that is Ex I caret, and the displacement, the small segment of the displacement dl is equal to dxi plus dyj plus dzk. Okay. Now the potential difference dV is equal to minus E into dl. Substitute the values minus Ex I dot dx I dy j plus dz k. Now the here is dot. I dot I is 1. I dot j 0. I dot k 0. So that is dV, the potential difference, the dV is equal to minus dEx into dx. Means the Ex, electric field with respect to the x-axis, Ex is equal to minus dV by dx. Similarly, with respect to the y-axis, Ey is equal to minus dV by. Similarly, Ey is equal to minus dV by dy, Ez dV by dz. Means we can say E vector is equal to minus dV by dr array. These equations represent the relation between electric field and potential.